Welcome to the session, Engaging and Inspiring Learners in Computing through Project-Based Learning. This is a professional development event for teachers brought to you by the Armed School Programme in association with the Central Board of Secondary Education. My name's Nick Sample. I'm Senior Manager of the School Programme at ARM, and I'll introduce our speakers shortly. I'd like to thank you all for joining us today. It's wonderful to see so many greetings and introductions in the chat already. I appreciate how valuable your time is. I hope you all find today's event useful. Just a couple of housekeeping points, which I will return to before we start the main session. If you have any questions throughout the session, please do put them in the Q&A box. I may occasionally post links in the chat to supplement the presentation, but because of the number of participants, please use the Q&A function for questions. Next slide, please, Rob. Okay, and here's the agenda for today, as you will have seen from the advertisement for the event. Before we start, I would like to thank CBSE, Dr. Saha, and Mr. Singh for enabling today's session. We will begin with a welcome address from Dr. Saha from CBSE before I introduce the school programme. We'll then move on to the main training session before doing Q&A, feedback and close. Next slide, please, Rob. Okay, without further ado, I'd like to introduce Dr. Saha, Director of Trainings and Skill Education, CBSE New Delhi. As I'm sure you're all aware, Dr. Saha manages the work of skill curriculum design, development of student resource books and training manuals. He also monitors the execution of various teacher training programs by 16 CBSE Centres of Excellence. Thank you, Dr. Saha. Dr. Saha, you're on mute at the moment. I'm not sure if you're.
Yeah, I am not able to start the camera. That's the problem I am facing. Anyway, without further waiting, good afternoon, all of you, all the panelists, especially Nick, Robert, then Surya, Apurva, my colleague Sri R.P. Singh, and of course a huge number of school principals and teachers who have joined us today in this special event of launching this project-based learning, and especially the computer science community. The way it is growing at this point of time in CBSE school, or even in the state-run school worldwide, there are some phenomenal interventions we have seen in the last 1 decade. And I can claim that CBSE is a front runner in all these initiatives, because when the top-notch university in Indian systems used to work upon Fortran 77. During that point of time, CBSE introduced C and CPP, and gradually Python in the computer science curriculum. And of course, now we are offering artificial intelligence. And the way the entire landscape of computing is changing worldwide, I think some way or others, we need to look into the new age technology. And here comes ARM, who has rather captured the entire consumer market and more than 50%, and it is somewhere near 70% the processor, the semiconductor related, whether it is cloud or in other ecosystems. And Raspberry Pi is known to almost all that and be here. So how these kind of emerging solutions can be really utilized in the Indian school system, so that our principal, our teacher, not only IT teachers, even the other teachers, how they can orient with these kind of technology, they can bring into the classroom, discuss, and gamified content they can create on their own, so that the understanding of any scientific concept, or for that matter, even if it is related to tourism or social science or any other ecology related issues, can really tagged into the project-based learning. I think ARM over a period of times became a market leader in this specific area. And let me welcome all of you at the same time. Let me thanks the ARM top management and the representative who are very much here, so that school to technology solutions provider, whether it is research-centric, innovation-oriented, or entrepreneurial activity, can really bring into this project-based ecosystems. So it is a proud moment for both the organizations, and especially for the school. Let us celebrate this launching event, and gradually, I believe Nick and Robert and others are going to deliver it on the technology perspective, and how teacher and student can together in a collaborative way really going to achieve the 21st century mandate given by different global solution provider, and how we can make the citizens ready to not only face the challenge, but to provide solution to the challenge. So we really aim for a problem solver, and that is possible with your wholehearted participations. And maybe this is a short event, and here in this through this kind of presentations and all, be participative, and a lot of comments and good wishes I am able to see through the chat box. And I believe after the presentations, you are going to put a lot of questions also. And there comes both Robert and Nick is going to address this issue. And gradually, if some things remains pending due to the paucity of time, we can again further fine-tune this agenda, so that it can be piloted in good number of schools, that the real essence of project-based learning we can promote in the ecosystems. So with this note, once again, let me thanks all the participants for joining us in this short notice, despite of the one-way pandemic and your regular schooling, but your interest is really giving us a different kind of positive vibe to all of us, and hope this would be excellent sessions ahead. Once again, let me personally thank Mr. R.P. Singh. He's actually coordinated well in time, and from ARM side, Apurva especially, but other panelists, of course, they are going to get the thanks from all our participants. Once again, let us open the sessions. I am handing over to Nick for further taking us through the journey of ARM.
Thank you, Dr. Sahan. That's that theme of the problem-solving mentality is one that we'll be touching on quite a lot of the time in today's session. So thank you for that very apt introductory notes. So okay, so now I'm going to give a brief introduction to the ARM school program. Next slide, please, Rob. So here is here's my colleague Rob and I. We are the ARM school program. We sit within a broader team called ARM Education. that addresses both schools and universities. So why was the Arm School program set up? Well, it was begun about 4 years ago, building on the work of our university program, which supports faculty and professors in keeping their computer and electronic engineering courses up to date. Next slide, please, Rob. The Arm School program enables teachers to inspire the innovators of tomorrow. As Dr. Saha has reflected on, the pace of change in technology is accelerating, and this really puts a pressure on education systems to keep up. We recognise the importance of industry taking an active role in helping to address this gap. We understand the work teachers do and its central importance in transforming the workforce and enlightening citizens, as well as decision makers of tomorrow. To make scalable change in education, it's absolutely crucial to support education systems, and most importantly, teachers who help young learners reach their potential day in, day out. So thank you for all you're doing to help shape the STEM and computing ecosystem. We really do appreciate all the work that you put into it. Next slide, please, Rob. As well as supporting teaching communities of practice in STEM and computing, the Arm School program has produced and continues to supplement a range of teaching and learning resources, which are all free to access, which you can find on arm.com/schools. The focus of these resources is on improving learner engagement in computing, using the pedagogy that Rob will present shortly, and ARM-based devices, such as those from Microbit, Raspberry Pi, and Arduino. We'll talk more about this later in today's training session. Next slide, please, Rob. We've also, as you may have seen from the advertisement for today's event, we've also recently launched a new program of professional development courses on edX.org. These courses take you on a full journey through how you can use physical computing devices to inspire and engage learners, covering topics such as pedagogy and assessment. You can enroll for free using the links provided in the event information page and in email reminders. And today's training explores some of the themes in our edX program. Next slide, please, Rob. So before I go any further, I would like to introduce my colleague Rob Lehmann, who will present the main session today. Rob started out as a network engineer before moving into teaching in secondary schools, where he led departments in achieving outstanding results in information technology and computer science. Rob then worked for Cambridge Assessment, reforming the computer science A-level and GCSE in the UK, and developing assessment used in several countries before he then went on to join us at ARM. Just a reminder, throughout Rob's session, please do use the Q&A for questions. So that's the Q&A box in the Zoom functions at the bottom of your screen. And to be clear, we'll only be answering questions in this session that are connected to the topic in this professional development. Anything that's off topic, I will put to one side, dismiss from the chat, and my colleagues in ARM India will handle the queries offline. Okay, Rob, over to you.
Thanks, Nick. And again, thanks everybody that's been involved so far. So welcome to this session regarding project-based learning. And I'm going to spend a little bit of time building the landscape about what makes up project-based learning and all the different elements that at the Arm School program we believe have to feed into making a successful project-based learning experience for any age learner. And to start quite simply, these are the key tenets about what makes up physical computing. First of all, you have the physical elements, such as the device itself, the network that these things plug into, the things that you have to physically touch to make these products and artifacts that we're trying to inspire these children to develop to solve problems. You then have the pedagogy, so how the teachers, this is everybody here, what they have to do to enable students to be able to come up with these artifacts and enable them to be able to develop them into a suitably complex stage, so it can actually solve real problems using data, using sensors, and using the physicality and the programming skills that we want them to demonstrate. There's also covering the core curriculum, so ensuring that if they're in schools, so they need to be able to cover the core curriculum in your jurisdiction, and so it's at the right level of complexity and depth to cover all of that. And they have to be able to demonstrate all of these skills, to be able to put all of this kit together, to be able to program it, and to be able to actually solve real problems. And all of this together is an amalgamation of the theory and practice that comes and makes what PBL really is. And during today's session, we're going to be exploring some of the theories that underpin project-based learning and how they have evolved and how they feed into the practice of project-based learning, and how these mutually support each other to create this wonderful pedagogy of project-based learning. And we're going to also, one of the themes of this, whilst this looks relatively simplistic, one of the things we're going to dive into is how complex project-based learning really is. And we're going to sort of skim across the surface and look at all the different elements that make up this, and look at some of the practical applications of some of this theory to ensure that everybody's doing it as well as they possibly can be, and are considering all the things that need to be considered. So breaking down that a little bit further, here is essentially the agenda for today's session, for this talk anyway, and these are the different elements that we're going to look at, and we'll check these off as we go through. We're going to look a little bit about the hardware and some of the electronics that goes into this. And this is the wonderful thing about project-based learning, is that it spans multiple subjects and multiple disciplines. It's not just about computer science, which can sometimes be taught in a very, very dry sense, and just learning how to program Python, for example, in idle, and some students don't really engage with that, and in others. But this brings together all these different subjects around electronics, network engineering, computer science, there's physics, and many others as well, including maths. And we try to structure all of these elements in a learning framework, such as IPO, which we'll get to a little bit later, and get students to make things. Then we'll look at some of the more pedagogical elements, how to cover the curriculum, how to engage learners through relevant context, which is incredibly important and is a key tenet of this, and really ensuring that everybody solves problems, because that's a key part of this. If your students can't apply technology and computing to solve a real problem, then it's almost a waste of time. And so it's getting them to apply those skills to solve real problems. And then through doing project-based learning, then we're going to be exploring the programming elements and the concepts, and how to adequately teach and enable students to express these computational techniques confidently. And through doing this through project-based learning, they will just learn things like design skills, Fullen's 6 Cs, which we'll come to. They'll have to do that creatively and do so collaboratively as well. And we, through the Arms Core program's resources, through our material, through our courses, we seek to support teachers to be able to do all of this all at once. There's an awful lot going on underneath the hood of what project-based learning is, and we'll have a deep dive into that right now. So first, a little bit about what computer or project-based learning isn't. I think in the classical literature and in education more broadly, project-based learning is sometimes dismissed as just simply using computers. If there is a computer or a gadget in the classroom, that's seen as physical computing. And that's a very, very simplistic approach. And I think there's a lot more to it. And really, as you can see on the screen there, though, there has to be a lot more thought into what the processes of learning using these devices and this technology. And ultimately, we're trying to use the technology as a stimulus to enable students to design and make these artifacts. And artifact is a key word there. They have to make something new, something fresh, using computers and technologies, and so that they can express these digital skills to solve the problems. And it's joining those different elements together that makes up what PBL really is. But essentially, they have to be making something. And you can see there from the pictures, you can buy lots of these consumer electronics devices where they simply plug them together and then they can program them, which is great and is a good learning experience. But if they're physically making a device from scratch that solves a real problem and is quite complex, then they can learn an awful lot more. So we'll look at now some of the hardware elements that go into project-based learning. We're going to look at some of the examples of technology which is out there and how that can be used through project-based learning to stimulate learning. So we'll start with the Microbit. There are obviously many different types of development boards out there, but the Microbit is one of the very popular ones. And we're just going to look a little bit now about what some of the inputs and processes and things that go into the Microbit. So on the surface, the Microbit looks relatively simplistic, but it comes built in with a load of inputs and outputs, which are very, very powerful and allow learners to use those to create some quite sophisticated devices and artifacts. It uses the Microbit version 2, which is the newest one, has some additional features such as the speaker and a microphone so that you can do some machine learning elements with it. It also has some additional buttons and lots and lots of connectivity. And the most important ones, which are on the version 1 Microbit as well, is like the accelerometer and the light sensor, which allows you to do all sorts of environmental monitoring and capturing digital data and doing something interesting with that. Also, because of the size of this board and the fact that it has lots of these sensors built into it, it allows it to be quite a compact package to use when creating these artifacts. So it's a really interesting device that you can do an awful lot with, and lots of our resources use Microbit as an example of the type of board that you can use to create these projects. That's not to say that there aren't other boards. There are many other boards out there on the market, for example, Crumbles and Raspberry Pis, Picos and Arduinos. All of these can be used to create similar sorts of artifacts, although some of them can be more tricky to use depending on the type of technology that you have available in your classrooms. But a lot of we have resources as well of projects using Picos and Arduinos and the various other boards as well. But we'll be, for the examples that we're talking about today, we'll be looking at the Microbit. But all of these projects that we're talking about today, and when you're designing your own, you can use any technology that's out there. And really, the point of this slide is to sort of express that the technology it doesn't really matter. It doesn't matter what hardware you've got, as long as you have some sort of physical device which is controllable, which is programmable, and you can use some types of inputs and you can use some sorts of outputs, then you can accomplish project-based learning using almost anything. And so it doesn't need to be necessarily board or technology centric. And it's really about the learning experience. It's about the creativity that you try to eke out of your learners through the projects and the problems that you provide them, and how they express that physically in the board, as I say, doesn't really matter. So one thing that's that you need to consider when introducing project-based learning, if you haven't already, is sort of the conception about what these physical devices are. For example, if you put one of these devices in front of a learner that's never seen physical computing before or never seen these devices, it can be quite confusing. It looks like a PCB, it looks like a circuit board, and that can be quite intimidating to work with. And a useful comparison, especially with the Microbit, is to compare it to a smartphone, something which many students will be at least vaguely familiar with, and they have many of the same features. There are buttons on a smartphone as there are on a Microbit, and you also have buttons on Pico and the various other boards as well. It has a capacitive screen. Obviously on a phone it's a bit more sophisticated, but you have the logo there on the Microbit. You also have the LED matrix which serves the function of the screen on the Microbit. These things have inbuilt communication such as radio and Bluetooth, which is exactly the same as a smartphone, and obviously a microphone and a speaker on the V2, just like a smartphone. So if they conceive of it as a device very much like a simplified version of a smartphone that you can program directly, that gets over the hurdle about what some of these physical devices are, and it allows them to be a little bit more creative in how they solve these problems. So the next little bit of the hardware, and this sort of digs beneath really some of the computer science elements. And now electronics and engineering and computer science all sort of meld together into sort of computer engineering or computing engineering when you get to university. But at the school level, that's not always dug into they're sort of kept separately in the subject domains. But it's really useful to explore some of those concepts when looking at what physically makes up some of these devices. For example, the LEDs, students may not have heard of LEDs before, but it's useful to look at what they actually are compared to a traditional light bulb and how they are used on a Microbit, and it allows you to dig into some of the math theory as well in terms of how these LEDs are arranged into a matrix and how they are referenced using X and Y coordinates, and then you you need to have at least a shallow understanding about what that means to be able to program them effectively. But because especially if you're using Python or one of these textually derived languages, then an understanding of that is essential, because you need to reference them directly. And when you're programming these algorithms, then obviously that becomes very, very necessary. And understanding how the electronics works around these is an interesting side note when you're talking about how these devices work. There's also the other sensors on there, and this is where you can get into the sort of the physics of how these things actually work. And you'll be surprised how many students are really interested in how these things work. It's how does a tiny little sensor, and these things are millimeters across, how does it sense acceleration? How does it sense how does the magnetometer work? And so using these sort of simplistic diagrams, you can look at how these very, very tiny electronics devices can actually sense the real world and turn it into a digital signal, which we then can interrelate or interact with through the programs. And again, you can dig into some of the physics around resistance and what that means, and how temperature can change resistance. And you don't need to dig in terms of the real complex levels of theory that you might cover in, for example, a physics or a maths class. You can just explain that these are the concepts that underpin this, and then it gives them a much deeper understanding about how the electronics works and how that relates to the real world. And giving some of this theory a grounding in the real world is really, really important. So those are some of the inputs that the Microbit and some of the various other electronics devices have. And it's really a core pillar of the ARM School program approach is this concept of IPO, or input, process, output. And this is crucial to understand, and this relates to everything from the design phase through the implementation phase and the testing phase when you're developing these PBL artifacts. And that you have to teach this to the students front and center at the very, very beginning, is that we're going to be taking inputs from the real world, be it temperature, light, electromagnetic readings or whatever, and then doing something with them, so processing them, doing some sort of calculation on them. Maybe it might be some selection. Sensing whether a temperature is above a certain threshold, for example, or it could be just storing it. And that could be the process there as well. And then usually there is some sort of output, either writing to a database, to a file, or it could just be something like flashing an LED. So, but having that sort of taking a step back and thinking about all of these systems, all of these processes involve some sort of input, some sort of processing of that input, and then some sort of output. And that's again how we link the real world to the programming elements within project-based learning. So it's crucial to understand this and to get students to understand this as well, how to impact the world through programming. So that's some of the hardware elements. And one thing I didn't mention there on making was this is why it's really important to have making as part of project-based learning, and having the students actually make these devices so that they can make that link between the electronic or the analog inputs and how that's being digitally thought about in the device, and then how that then interrelates with the external world. And we'll look at some examples of some artifacts and some projects that you can do a little bit later on, but we have many examples of these types of projects in our resources, but we'll focus just on the theory now. So next we're going to explore some of the computer science that sits or underpins these elements. So you have the physical device. We understand that it's part of a system, and that it's you have to understand a little bit about the electronics and the processes involved. And so let's now dive into some of the computer science elements. So programming these boards can offer a number of challenges, or there's different ways of interacting with them. You have, for example, with the Microbit, you have block-based interfaces such as the MakeCode environment, where learners can program their devices using colored blocks, and then you have the more textually derived and more formal way of programming them through like a MicroPython IDE, and there are many others as well. Obviously, the Arduinos, you have to program in C, which is obviously a completely different language to Python, and so you have to really be sure when you're starting to use project-based learning as to what IDE do you need, and is that installed at your school, and that sort of thing. So there's a few technical things you need to consider, and there is also using textually derived languages can have a bit of a steeper learning curve as well, because you can't throw them into a programming project if they haven't learned how to program. So there's some precursor learning. But what we found through years of seeing this in schools is that using block-based interfaces, and there are examples of block-based interfaces for all the developer boards that I've come across, is that even students who have never seen these interfaces before and they've never programmed, you can give them a simple problem, and then they can solve it using the blocks. And just the sheer fact that it's not textually derived and that it has these colored blocks that they can drag about, it allows them to engage with and interact with some of these quite complex concepts that they can then apply and solve problems programmatically in these block-based interfaces, and then put that code onto a board like a Microbit or whatever, and you know, solve real problems. And it's amazing to see how far you can go without even having to formally teach them. Not that I advocate for not teaching computing up front, because that would be foolish, but you can go an awful long way and push the boundaries using block-based instead of text-based languages, and then transition to text-based languages when that's right for your learner, and that's where the differentiation comes in. And when I've seen students working on this of similar abilities, and some using text-based and some using block-based, you can add a lot more functionality a lot quicker for using block-based languages, because you can treat it as more of a rapid prototyping tool rather than getting lost in the syntax and focusing on the coding bit of it. And whilst that's vitally important, especially for computer science, the purpose of using these languages and these tools is to teach the students to be confident applying the computational techniques, not necessarily just getting them to type in lots and lots of syntax. And they can do that quicker through block-based languages. And there is a move in sort of computer science education, certainly in the UK, and it's growing internationally as well, in the sort of middle school, sort of in the up to GCSE levels, up to sort of 16 years old, is using more block-based languages in lieu of text-based languages, because you can just learn more quicker by using that, and you can unpack some of those complex computational constructs much simpler, and students understand with it and can engage with it much easier than doing it in Python, which adds in an additional learning curve of the having to deal with the syntax and indentation and all of those sorts of things that you get with more formally typed languages. Never to mention the formal structure of languages like C, which are even harder to engage with. So just an interesting tidbit there from the computer science world is that the block-based elements, whilst easy to dismiss as being trivial because of the sort of coloured nature of it, I suppose, in terms that they tend to be quite colourful, but you can actually go quite far and do some really complex stuff. And we have some good examples of some more complex projects where they express all of the computational constructs required for the UK GCSE, which is equivalent to obviously international variants. And you express all of those in such a complex nature that it would be relevant for a 16-year-old to be doing. So it doesn't necessarily need to be simple. So yes, you can go an awful long way with block-based coding, and you can speed up the PBL process by not focusing too much on the textually derived nature of it and just using it as a tool to speed things up. And so where does all this come into it? So we talked a bit about the hardware and how that creates the input elements of it, and then as we've just been talking about all the different computational constructs, so sequence, selection, iteration, and how all those fit into the processing bit of it. And this is really important when teaching using project-based learning, is to get students to at least have an understanding about what these three elements are and how they can apply them to solve problems. And that's the key bit of this. And students can learn this through just through sort of experimentation, but if you teach them this in the abstract and then show them how to apply it to a real problem, it's a really, really powerful tool for them to understand how to do this, especially with sequence and selection. For example, if you have a device where you want to program it to show something on screen or play a sound when you press a button, you have to make sure that the sequence there is correct. It doesn't show the output until the input is triggered. And especially when you start getting into applying computational logic and you're using ifs and things like that, so sensing an input and seeing whether it meets a threshold or not, then you need to start introducing some quite complicated selection, and then you can use iteration for various more complex things. But students need to be able to apply these things not just to understand how selection and sequence iteration work, but what does that mean when you're having to deal with that using digital data, and what does that mean in terms of taking it in, doing something with it, and then spitting something out through the output, and that's the key bit of it, I think. And then in many computing classrooms, especially with non-specialist teachers, this is where there's a disconnect between the theory and the real world, and that's the bit that by doing this well and teaching these computational constructs through project-based learning, this is where it becomes a really powerful tool, and students learn how to apply this much more confidently if they're doing it in a problem, in a project that they can engage with and they can relate to. So doing something in the real world, and that's again a core tenet of project-based learning. So sticking with the theme of the microbit and the blocks that it's got there, I just want to link together the blocks that are available and what that means in terms of IPO. So the basic blocks allow you to control the output. There are lots and lots of inputs from all the various different sensors and lots of different outputs as well in terms of some of the more fine-grained tools around music and the LEDs. You can do some really interesting projects with the radio functionality, and all the different development boards have got things that you can plug into them to add this sort of functionality, be it LoRa or Bluetooth or Wi-Fi or whatever. And so you can turn these devices into IoT nodes and transmit data between them and do all sorts of really interesting IoT projects using these quite simplistic development tools such as MakeCode. And then you have obviously the core computational elements around loops, logic, and variables, all which allow you to process some of that and do some really interesting projects using that. And you can teach again all of the computing constructs relative to the age range, as well as some quite interesting theory around maths and also physics. So there's you can do an awful lot with quite a simple palette of tools available through the various coding interfaces. So why does using these colorful blocks matter? Why does it make it easy to understand? And this is where we get back to the very nature of text-based languages and why it can seem a little bit abstract to learners, especially if they're coming to this from knowing nothing about computer science. And typically, when you see this sort of stuff taught, is they'll introduce one of the concepts, for example, selection, and then they'll be given an example in their language. As you can see, there's an example there in Python, and it solves a problem. For example, there you have variables introduced, then you're using some logic to see whether a condition is met, and then it'll print something. And whilst that does demonstrate the computational construct, it doesn't do it in a way that really engages the learner, and it doesn't really, whilst it might make sense logically, there's no sort of tangible link to the real world. You can't think, okay, I can now go and use this to solve a problem, to help me, to go and get a job or something like that. It just, that link is missing, and so they can't relate to it. And if they were then challenged to apply this construct in a completely different scenario, many students would struggle to do that because they've learned it in a particular theme and in a particular context, and so it's difficult to reapply that confidently, especially in like exam situations, which is obviously, as teachers, we want our students to be able to do confidently. So by teaching these elements through project-based learning, and especially through using block-based tools, is that you can relate this to the real world. And there's a very simple example there of using a loop with some selection and sensing the temperature. It's doing a logical test whether it's above a certain or less than a certain threshold, and then there is an output, and students can instantly relate to that. All students can sense the temperature. They're familiar with things like air conditioning or fans and that sort of thing, and so they know that this is how this logical construct can apply to the real world, and it's instantly recognizable and it's instantly familiar. And so that's a much more effective way of teaching these concepts outside of using formally derived languages. And you can then go on to teach how this is then expressed through Python, but it's this using the real context, the real world, and something that's relatable as an intermediary step, which is the important part of PBL and also block-based languages. So here's just another example of how to structure something slightly more complex and how it relates to the input process output model. And what you can see in the example there, that it's taking inputs, it's creating variables, and then it's introducing some loops there as well, and it just shows you how to link these things together, and comparing block-based constructs to the textually derived version of it is a really useful bridging tool when you want to move students away from block-based and into formal code. And you can show that these structures are very similar. It's much easier and quicker to drag blocks around than it is to type all of this out and make sure that everything's indented properly, especially when you get to the show. To the basic show LEDs bit of it, we have to type in all of the elements manually, which can be a little bit frustrating, especially for learners when they're trying to do things really, really quickly. So yes, it's a useful teaching tool to compare block versus text if you should do that, but that's only useful if you're doing that at a certain age range when you need them to be able to use textually derived languages, for example, in the exam. So that's some of the programming elements and how they sort of relate to project-based learning, and that's the very sort of the very simplistic elements of it. Just the core computational constructs, and they can be used to do anything. And this is where this sort of creativity element of project-based learning comes in, because you can apply these constructs and these practices to do whatever you want. There are thousands and thousands of different problems that they could apply these things to, and it's just a case of coming up with and designing and building learning experiences where students can apply these constructs and these theories to solve real problems. And that's something we're going to dig into now, is how do we teach them to be able to do this effectively, and also cover the curriculum at the same time. So we're going to dive a little bit into the theory elements of this now. So we've laid the foundations in terms of the electronics and the hardware and some of the computer science bit of it. And this is a very complicated diagram called the learning landscape. And this is all of the theories, practices, pedagogies, ideas, orthodoxies that underpin all of project-based learning and physical computing more generally as a concept. And this is all of we explore all of these in our edX course, which is obviously much longer than this short course where we're just going to glance across the top. But it's a very, very rich and vibrant world of all sorts of interrelated practices and theories. And if you want to explore more of this, then please do check out the edX course through the links and look at a little bit more of those. But today we're going to focus on the big three. So we're going to look at cognitivism, constructivism, and a little bit about behaviorism as well, and how these things as sort of standalone theories support the use of project-based learning to enable teachers to teach this effectively. So we'll start a little bit with cognitivism, and this is where it all began. And it's this idea as put forward by Piaget and Bruner and the likes about how do students learn? What does it mean to learn something? And how do they come up with the sort of the mental constructions and this schemata of applying and understanding the world around them? And this is where frameworks like Bloom's came from this whole notion of cognitivism. And Bloom's is something which is obviously I hope every teacher is aware of, and is used to sort of start from the very simplistic recall, sort of the very bottom of this, all the way through to thorough evaluation at the top of the Bloom's taxonomy. And it allows us to sort of segment understanding and be able to assess understanding at various levels of complexity. And we can apply that to project-based learning. And we can, through the nature of them starting with a problem and then decomposing that problem, analyzing the problem and solving the problem, they naturally move through Bloom's cognitive domains and naturally express the evidence to be able to show that they've gone through that. And so it's really, really important to have a conception about what some of these frameworks and some of these theories are, so that you can see them being applied in real time. Because it's often easy to dismiss project-based learning as just learning through playing or just discovery learning. And that can be seen as very, very simplistic, where you just let the learners fiddle with technology and they somehow learn by osmosis. And really there's a lot more going on underneath that, and students come up with these mental models and they develop their learning skills and cognitive skills through not just play but also structured play, and coming up with a framework of how they can apply that to the real world. So it's the only issue with this is that it's easy to, or criticism rather, is that it's easy to use this in quite a reductivist sense and simply say, well, we need to teach everything in a very didactic fashion, which is kind of one end of the spectrum. And this is what's led to much of teaching and learning historically has been chalk and talk, with teachers stood at the front of the board, classroom writing on the board, and students sort of, writing down and learning, whilst there are other and better ways of enhancing learning through experience and through play. And so this is sort of where education starts with this idea of cognitivism. And then that sort of evolved and grew into this concept of constructivism. And it goes the complete opposite end of the spectrum, and it rejects this idea of didactic teaching, and it relies more heavily on this the behaviourist approach of active learning. And this again attracts criticism, where constructivism isn't what I don't think should be considered as just learning through doing only. And there's very little evidence to show that learning purely through play or learning purely through experience is effective on its own. And I think this needs to be conceived of as a tool to enhance learning, rather than just a complete pedagogy in and of itself. Students can learn through discovery. They can learn through working with other learners. That's part of group work and all of that. And you'll see this through project-based learning. But it's not just something, you can't replace an entire curriculum with the constructivist curriculum and just let students learn by osmosis, because that just simply doesn't work. And I think we've all seen that. Some students, you can let them play and they'll learn and they will progress. Others won't, and they need a bit more motivation, a little bit more stimulus and a bit more scaffolding to be able to progress effectively. And so I think we need to be conscious of these concepts and these theories, and then just take the bits that work and then pull them together into what underpins what it makes up an effective learning strategy, which is PBL. And so that's sort of the opposite end of the spectrum. And then you have constructionism, where this is where the theories of like Papert and Piaget really start to bring these things together in terms of this, actively constructing learning. And it's more of a sort of a student-centered approach. And the only issue with this is more of a learning theory, and there's very little empirical evidence to suggest that this is incredibly effective. But project-based learning, as used out in the wild, has demonstrated this is an effective way, and it's that sort of middle ground between the other two elements. And it's sort of a mishmash of the two. But and this is an element, or rather the theory, that we apply quite heavily in project-based learning. So where does our schema and our pedagogy sit on that spectrum? So it's very much in that last camp. It's that we use elements of didactic teaching. We use structured projects to guide learners along a sensible learning path, but it's also relatively open, and we design our projects and our problems that we give to our learners so that they have an open-ended output, but to get all students up to a certain level, and to ensure that all students are being brought along on that journey. There are scaffolded parts to these projects that students need to engage with to make sure that they're all moving along this pathway and learning something. And that's where this is why project-based learning can be quite difficult to explain, because it's not completely didactic, it's not completely open, it's kind of somewhere in the middle, and it allows teachers to use the scaffolding tools and differentiation to effectively cater project-based learning experiences to the needs of their learners. And that's what makes it powerful, and also quite can be difficult to apply because there's so many different moving parts and so many different levers that can be applied to change the learning depending on what's right for your students. And that's really the skill of being, part of being a skilled teacher is being conscious of those levers and those variables, and being able to manipulate them effectively to really eke out every little bit of potential from your students to ensure that they're moving along. So this is just one more bit of theory I want to cover. There's this concept of Semantic Waves, and this is doing the rounds and is very, very popular at the moment in UK curriculum design. And it's again, you can see how this can be used to describe learning through project-based learning. So the idea is that you start off with an abstract concept, for example, selection or iteration, and then throughout the course of the lesson, this idea is unpacked. And it is explained using concrete things. For example, if you give them a real-world project where they have to solve something, they can then relate that abstract concept to that concrete thing that they can really understand, for example, the temperature sensor that we talked about previously. And then you give them an activity where they need to apply it. So they're not simply just relating two things together, they're having to actively engage with this concept and apply it to something novel and unusual, which they may not have seen before. And then through the course of that experience, they then have to repack that and then move up through that Bloom's taxonomy to evaluate what they've done and does it express that abstract concept effectively. And that's where you get that sort of curve of learning, going from abstract to concrete to application and then through to understanding. And so it's a really relatively simple way of showing how using real world context is a really, really powerful tool to understanding some of these more abstract notions. So I think that's quite an interesting diagram when you're thinking about the more ethereal nature of project-based learning. So practically applying project-based learning is the next step, and this links back to the formal computer science curriculum as well, and also through to industry, where all projects, there has to be something real and there has to be some sort of tangible output, and that output has to be designed. And it all starts with some valuable success criteria. So what are we trying to achieve? What are we trying to do? What is the problem that we're trying to solve? And all of our resources, you have success criteria which are designed to be progressive. They start off with quite simple, easily achievable goals, and then they ramp up in complexity. We expect students to then plan and design a solution to that, and that could be something as simple as doing a flowchart or filling in a design table, maybe an IPO table, so getting them to think about what the inputs, processes, and outputs are. And then once they've done that successfully and they have a sense of what the problem is that they're trying to solve and how to do it, they then start to develop it. And there's always a well, the students always want to jump straight into developing the solution rather than thinking about the planning and the designing bit of it. So it's really important to get students to think about the problems before they start to develop a solution. And that's crucial, especially when they want to get into the world of work and where planning is crucial. And then likewise, there's testing and remedial action. Now, testing doesn't necessarily need to be formal. It can be done just through experimentation. And as they're trying to solve their success criteria during the development phase, they will naturally be testing their solution constantly. So they'll put their code on their Microbit, for example. Does it do what I expect it to do? If it doesn't, then you have to go back and troubleshoot and bug fix. And so you're naturally going through that testing and remedial action cycle over and over again. And then at the end of the project, getting them to think, does my solution that we've made collectively as a group, does it meet all of the success criteria? And that's where you go through the full Bloom's taxonomy. They're evaluating their complex solution to a complex set of criteria. And so that's where it becomes a really valuable learning experience. They've made something concrete, something tangible, and they've applied abstract concepts through computer science and electronics to solve something real. And that's that's why the iterative development cycle is really, really important. And it also helps to segment learning into lessons, for example. So you could have getting them to think about the success criteria and plan and design it in one lesson, and then develop it over another couple of lessons, and then doing the testing and evaluation in a separate lesson. So it helps to break up that into something which is more manageable, or even all within one lesson, depending on the size of the project. Because projects don't necessarily have to be huge. They could also be a little bit more bite-sized, depending on the age, prior experience, and ability of your learners. So that's the sort of some of the ideas around covering PBL. Now we'll have a look at these slightly more abstract concepts around design thinking, creativity, and full and 6 Cs, and some of the more practical elements as well around delivering project-based learning. So design thinking, this is, so we mentioned this before as part of the design phase of the iterative development cycle. And in our resources that we give out, we provide these design templates. This helps structure and scaffold this design process for learners. Because if you just say to learners, here's a problem, go and solve it, you know, it can go off in all sorts of weird and wonderful directions. Students can be incredibly creative, and it helps to constrain some of the elements and variables in their problem solving. One, to keep it on track, and also to keep it in the realms of reality. And so giving them this scaffolding is really, really important, because it helps them all think about things in the same sort of way, and it also helps them interrogate things that they wouldn't necessarily always think about. And in its simplest form, an IPO table is a really useful tool, because you get them to, again, think about the inputs, the processes, and the outputs, and getting them to think about those separately is really important as well. So conceiving of the inputs through the how, or rather what that input is and how is it measured. So for example, with the temperature sensor, it would be reading the temperature in Fahrenheit or Celsius, and then how is that data processed, and then what output does that link to? And in a typical project, you'll have multiple inputs all happening all at once. And so it's really important that they think about all of those, and how does that input, how it's processed in the output, link to the success criteria. And that's the important bit to get right. And that's the challenging bit of project-based learning, is how do we navigate and how do we structure our inputs and our programming to solve a real problem. And that's an important thing to think about. There's also a nice link to the real world and industry as well, by thinking about how you can productize these assets that you're creating. So if they're creating a, let's say like a pet or a device or a product that's solving a particular problem, thinking about all of the things that go along with that. For example, how would you design the case? How do you design the thing that the board sits in? What's the branding behind it? You know, what materials are you using? What are the power constraints? Is it waterproof? There's all sorts of other things you need to think about. Taking leave from our design and technology and engineering colleagues, how do you ruggedize these products to make them suitable for where they're going to live in the real world? And getting students to think about that in a group is really, really interesting. So they have to think about an awful lot of different things. For example, how do you market this product? If you were trying to sell this product, how would you do so? How would you describe its virtues? What are the unique selling points for your particular product? So it's all of these sort of things that sit around the outside of developing products, you can get them to think about as well. And that's what makes it not just cross-curricular, but it also lets everybody in a group that's working on a product contribute meaningfully. And these things also feed back and forth. So for example, if one of the success criteria is to make something really, really rugged, that might limit the amount of inputs that you can have, because you don't want the electronics showing, for example. So these have to sort of feed into this iterative development cycle to make sure that the success criteria are being met effectively. And so design thinking is a really, really, really important element of this, which is often overlooked in computer science. And it's not just the programming bits that need designing, it's also the physical aspect as well. And that's also what makes these projects fun. Students love making stuff, and it might even be as simple as paper, cardboard, sellotape, glue, that sort of stuff. It doesn't have to be complex. We don't have to be using metalwork or wood or anything like that. It can be, keep it simple, and it's a really important message to take away from this, is that, you know, keep it fun. So, and why does it matter? Why is it you know, this also is another reason why some colleagues may see the making element of this and trivialize it to a degree, but by getting them to think about the outputs and having the physical element that they're designing solve a real problem, it develops this engineering mindset. It makes them understand what the constraints are of the real world, and also, you know, again, understanding trade-offs as well. And you can even add, as part of the learning experience, some sort of budgeting element into this, where they have to like buy elements, and you give them adding additional constraints there, and that can add in an additional layer of complexity to project-based learning, which can enhance the learning, and also closely mimics the real world. You know, we don't have infinite budgets and infinite resources when you're designing a new product. So it can be quite entertaining and engaging for students to have to think about these things in that kind of abstract sense, and it's not just applying computational constructs. So when they're doing all of this stuff, and obviously there's an awful lot going on, you know, they're having to design things, they're having to think about problems, they're having to think about electronics, they're having to design all sorts of solutions to those. And it works really, really well to do these in groups. You don't necessarily have to do project-based learning in groups. It can be done in isolation. That's not a problem, but it works better, and it's much more engaging when students do work together. And we advocate for small groups, sort of like 2 to 4 learners. It's nice if there's a gender split as well, although that's, it doesn't have to be essential. But whilst they're doing that, they tend to, and especially when they're solving a complex, tangible problem, is they express these Fullen's 6 C's here. So, you know, when you give them a context which is truly global, then you're enhancing their ability to become global citizens. You know, they're solving real problems. For example, if you're getting them to create something which solves pollution or something like that, you know, they have to think about how does it impact the real world. And in order to solve these problems, they have to be able to communicate effectively. They have to be able to talk to each other, to be able to realize what the problem is and how they can apply the tools and the things that they're working with to do this. And they also have to be able to communicate what their solution is externally. And this is where adding in these kind of business elements as well, where they have to come up with branding and marketing and a unique selling point. And that's where the communication bit comes in. They're obviously applying critical thinking skills, because they have to not just deal with resource constraints, but also deal with the limitations of the hardware that they're playing with, and also how to apply the computational construct when they're programming their development boards. And in order to do all of these different things and all of these competing pressures, they have to be creative and do that collaboratively, which can be quite challenging. Not all students naturally want to collaborate with their peers, and trying to get them to do that in a structured way is really, really healthy. Again, it helps build character, and it helps them learn how to learn effectively. Not all students need to be experts in all of these different fields. Some naturally gravitate more towards the programming, some naturally more to the engineering, some more to the branding and the more the softer skill side of these sorts of things. But they all have to come together to create this end product that meets the needs of the user, and that's really important to keep in mind. So that's a very, very brief introduction to all of these different elements that make up what project-based learning is. And really, this is just the starting point of what project-based learning is. This is a sort of very condensed, simplified version of what project-based learning can be. And this is really just some of the theory and practice that underpins all of that. Never mind what these projects actually are, which we'll look at in just a second. Because whilst all of this theory makes sense, it's good to see it in the real world and think, how can I actually apply this theory into my everyday practice? And this is where the ARM School resources can help you. Our resources are designed to, you can take them off the shelf and use them straight away in the classroom, which is great. They're also very, very open, and we apply a design tool called the ASP schema, which allows you to create your own projects and use whatever context is right for you, and to apply all of these different elements that we've been talking about into your classroom in a way which is relevant and engaging to your learners. And we'll look at how to do that in just a second. So this is our schema, and this is something that we cover in depth in the edX course. But it's quite simplistic in its approach, but I'll just explain what all these different elements are and how they fit together. So the bit in the middle, those colored squares, these are the core building blocks of our pedagogical approach. So the getting started bit is where we lay out the context, where we say what the problem is and how it relates to the real world. And then we lay out the success criteria. You'll recognize this from before. This is where we set out our problem set. This is where we set out what learners have to do and these building complexities. So it starts very, very simply and gets more and more complex. We then offer pro tips. Now, these are little sort of call outs and bits of scaffolding where we're aware where learners may typically trip up or maybe struggle, and we offer support resources. It may be like a code snippet, it may be just a tip, and that helps guide learners on that learning path. And then they go through this iterative development process to come up with a solution that meets these success criteria. And then we have stretch tasks, which are essentially additional success criteria, but they're more open-ended. So if you've got some very high-flying students who are very, very able, then and they finish the project very, very quickly, you can then keep them on track, making sure that they're deepening their learning of that particular context or subject area. without necessarily going off track and becoming disengaged. And then for the evaluation, we have what's called the final thoughts, where we get students to reflect upon what they've done, how they've met the success criteria, how they've applied that knowledge that they've learned throughout this process or previous learning to solve that problem. And that, again, you going up through the Bloom's taxonomy as you go through that and get them to reflect and evaluate what they've done. And we express all of these, this schema through all of our courses and through all of our resources. And you'll see these headings crop up in everything that we do, including our CPD. And that can be expressed through, for example, lesson plans. We've got slide decks for all of our resources, worksheets. The cheat sheets are essentially code snippets, which can form part of the pro tips, for example. We also have teacher solutions in many of our resources as well. And so you can take this stuff off the shelf and use it, and you can adapt it and do whatever you want with it as well. So that's the sort of how we structure our learning experiences and our training. And it's important to just have a conception of that so the rest of it kind of makes sense. So let's have a look at a quick example. This is what we call the Microbit, and this is personally my favorite project. This is aimed at younger students, obviously, sort of middle school and below. And the context there, you can see setting the scene, is they have to create a pet. They're having to create a pet which is interactive. It has to be digital. And the key bit there is that last line, the pet must be interactive, and that opens up a whole world of complexity. How do you make a toy with sensors on it interactive? How do you take a digital or an analog input, compute it, IPO, and have some sort of output to make it interactive? And so there's some ideas there in the success criteria where, first of all, they have to make the pet, and you can see we've got a net there in the top right-hand corner, so they have to understand how to physically cut out and fold and glue together the pet. They have to be able to stick the microbit inside of it, and they have to decorate it. And so that's where the sort of the making bit comes in. And whilst this is relatively simplistic, this is for younger students, but you can have some really complicated elements that come off the back of this. For example, using like the radio transmission between the different microbits. I mean, think about how an accelerometer could be used, for example, as well. So a pet may not like to be shaken. So if you pick the pet up, it can sense that it's being picked up because of the accelerometer. And if you shake it vigorously, it can measure across different Gs. So if it goes above 1 G, for example, it may not like that. And so how could you turn that input into an output? So if Gs go above certain threshold, then show a sad face, for example. You can introduce concepts like variables. So you could have a variable for attention or hunger, and these variables can decrement over time. So it slowly gets bored or slowly gets hungry over time. And then you have to figure out ways of how do you feed or entertain your micropet. So again, using inputs to change variables programmatically, and that could be through pressing buttons or whatever you want. And this allows students to be really creative. A good example there is the little dog that you can see there in the middle, and they used a second microbit on the bone. And so that there was a food variable on the dog, and it went down over time, and it would get hungry, and then when it got hungry, it got sad. And so they made it so that the second microbit transmitted a radio signal, very, very low power, so that it had to be very, very close to the second microbit. And then when the bone microbit was near the dog microbit, it recognized that it was near it, and then it incremented that food variable. So it was like feeding the dog, and so that was and they were not prompted to do that. That was something that the students come up with on their own. So that's a really nice, fun, playful way of doing a project, and this can be done in a single lesson or over a full day, and you can stretch that out depending on the amount of challenge that you give your learners. And you can say 1 interaction or 10 interactions. It's scalable. And again, there's some of the ideas which I mentioned. So feeding and sleeping and getting it to react to temperatures, for example. You could use the features of the V2 microbit or any other electronic device, getting it to have sounds. It could snore, it can squeak, it can yelp, all these different things. So it's a really fun project. So whilst that the context for that is obviously people being in hospitals, there's a whole rich plethora of other contexts which make things more real to students, and these are the global goals, and we use these as a foundation for many of our projects. It's because they are instantly recognizable, and they make a difference to everybody on the planet, and it makes them, you can create some really, really engaging projects here. For example, having ones around quality education or around saving the environment, for example, challenge 14 and 15 there are really good for project-based learning projects. So, you know, dealing with like ocean pollution and pollution on the land. And we'll look at an example of that in just a second, but there are underneath each of these 17 goals is many other challenges in there which you can base your projects on. And I implore you, if you're playing around with project-based learning and need some contexts, these are a really rich source. So let's have a quick look at a more complex project. This is the oil spill cleaner upper. This is available through the micro course book on arm.com. And the challenge that the students are given, and this is good for middle school and upwards, because it involves slightly more complex problem set. But the problem is oil spills. You know, everybody's familiar with what an oil spill is, and you've been challenged to come up with designing and making a fleet of boat drones that drag around a smart material which can soak up the oil and effectively get rid of it. And so, you know, that's the challenge. They have to not just build they have to build a boat. They also have to make it so that it's it can be automated and it has motors, so it can actually go around. It has to be able to navigate the ambient conditions of the water. So there's a whole host of problems there that students have to overcome. And in its very simplest form, it can be started with a button press, and then it has to follow an algorithm. You know, how do you programmatically get a boat to go up, down, left, right through this pattern to clean up the oil, whilst dealing with the ambient conditions of the water? You know, water is wobbly, there is wind, the boat can spin around, there's all sorts of things that can go wrong. So there's lots and lots of things that the students need to think about, the least of which being not sinking the device and it breaking. So you can see here we're using an algorithmic problem that students have to solve using IPO and electronics, and this is where it really brings together all of these different interesting elements around project-based learning. They also have to think about some of the engineering problems with this as well. So how do you power the boat? How do you get it to turn? Students tend to naturally want to have a single motor on the back of the boat, and whilst that would work in it going forward, you can't get it to turn. So using paddles is an interesting problem. And what we found when we did this live was just getting the paddle to stick to the motor in and of itself is an interesting challenge, and they have to think about what materials that they use, and things have to be waterproof and the like. So all sorts of interesting problems that students have to solve. And when you come to the stretch tasks for this as well, if you've got some very able learners, or you're doing this with more advanced students who are older, getting them to have multiple versions of this drone. So how do the drones talk to each other? How do they communicate and work as a mesh network, and how can it cover a wider area? So you can get quite sophisticated with this problem, and you can use this with, or it's a good example of how you can use this with young learners and really old learners, just by limiting what resources you give to them. So those are a couple of examples of our resources. You can find all of these on school.arm.com, amongst other resources we have there. There are courses and resources for Microbits and Arduino, and very soon Picos as well, which are the Raspberry Pi. We also have some YouTube channels where we go through how to program using MicroPython and the Microbit. So there's a whole host of stuff there that you can engage with. So one last note, because we're coming close to time, is how to use PBL across a semester or a term. How do you bake this stuff into your formal planning? Because whilst PBL can be a really fun activity, and you can do it in a single lesson or across a full day or something like that, it shouldn't necessarily replace your entire curriculum. And we've had discussions about this in other forums where teachers are very reluctant to sort of abandon their traditional didactic teaching methodology. And so what we propose, or what we suggest really in our schemes of work, is you start off with a baseline assessment to see where your students are, although that's not always necessary. Then teach some theory, and that can be done in a didactic traditional fashion. And there may be 2 or 3 lessons where you're teaching them the core theory. You can make it fun and make it engaging and use the context and the like, as we do in our resources, and then get the students to apply that learning through a project. And it can start with a small project and make sure that the skills that they're demonstrating are the ones that they've learned during the didactic theory lessons. Then you have more theory lessons after that project where you build on that and you go more complex. And then you have a bigger project where it might last a full day, for example, and then you build on all of the previous learning. So you're getting them to express all of the learning that they've done in more creative and more in-depth and more sophisticated ways. And that's the real power of using project-based learning in this way, is that you can push students much further than what they would do in a traditional classroom setting. And then at the end of that, obviously, you want to assess them. And you can assess project-based learning. That's one of the criticisms of PBL, is that it's difficult to assess. And it is, but it can be done in a number of different ways. And it can be used to enhance formal assessment, depending on whether you're using this to teach sort of formal academic qualifications or not. There are some problems around validity and verification using project-based learning for assessment, but we very much conceive of it as a tool to enhance learning rather than being a way to assess it more formally. And we have an entire course on assessment of project-based learning as part of our edX offering. So hopefully that's painted a picture about what project-based learning is and all the different moving parts that go into it. And there is an awful lot more to be said about all of these, and we go into this in a lot more detail in our edX program. And again, this is the learning landscape, and it's just I want to show you the depth and breadth of all of the elements that make up what PBL is. And hopefully this has sparked an interest in yourselves and wanting to look at how you can use this as a teaching tool, and just be really conscious about how complex this is and all the different moving parts. And so thank you very much for listening to me today, and thank you very much. And I'll hand over now to Surya for the feedback.
Thanks, Rob. Just before we do that, Rob, you can have a glass of water now after that. And, yeah, thank you for doing that. So we'll move on to Q&A in a moment, and thank you for the questions that have come in the Q&A box during Rob's session. But first, I think we'd like to cover feedback. So just hand over to Surya, our colleague who handles operations in ARM Education India since 2019. So Surya is a great member of the team. She strives to expand her learnings, knowledge and skills to achieve operational excellence, and certainly done that today in her support for this event. So she'd like to talk to you briefly about how you can provide feedback for the event, which we'd really love to see. So over to you, Surya.
Yeah, thank you, Nick. Good evening, all. I hope you all enjoyed the session. I have shared the feedback form in the chat box. Please let us know your feedback about the event in the feedback link. You can also copy and save the link if you want to share the feedback later.
That's excellent. Thank you.
The link is available in the chat box.
Thank you, Surya. So I think hopefully everyone can see that, and we'd certainly love to hear your feedback, which you can complete as we're going through the Q&As. So I'd suggest at this point we move on to that. Okay, so some fantastic questions that have been coming in over the course of the session. What I've tried to do is to group them thematically so that we can talk about, address, a number of them at the same time. So firstly, from a practical perspective, there were a few questions about the PowerPoint deck and the recording. So we will certainly aim to get the recording of the event and a link to the deck out to everyone who's attended, so you can review that in your own time and use it as you feel useful. And then there were also a couple of questions about what do you need to implement this practically within the classroom? What's the cost? Where does it come from? So I think I'm going to pass that over to Rob from a sort of numbers perspective, but I'll just mention that in terms of resources, you can go to our web pages that Rob provided the link for. That's arm.com/schools, where you can find all of the resources that Rob's referred to free of charge. And the hardware that Rob has referred to, the Microbit has been a big part of the session, but also Arduino and Raspberry Pi. These are boards that are based on ARM technology, so the processors within those boards are ARM based. ARM itself doesn't sell those boards. those are sold by the organizations that develop them. And you can find the distributors for those boards online. So I think for the Microbit, it's element 14, and a Microbit would typically cost, I was just looking this up online whilst we were doing the session, it's in the region of 1,200 rupees. Now at the moment, they aren't available online, I can see. There has been a bit of a disruption to the supply of Microbits and other boards, and also, as you may have heard, other products that rely on microchips because of a global silicon shortage. But we understand that this is, for Microbits and other boards, this is playing through now and should be available through distributors in the next month or so, all being well. So that being covered, Rob, from a sort of classroom setup perspective, what do you need to give this a go?
I think the simplest and easiest way to do it is to use group work. For example, if you're doing the Micropet project and you had students in groups of 2 or 3 or even 4 students, for example, then you would need 1 Microbit or 1 device per group, because they don't need to have 1 each for that, which reduces the cost dramatically. If you have a class of 30, you just subdivide that by 3 or 4, and so you need 10, 15 Microbits to make that work. It's always worth having a spare, but a classroom set typically is about 15 Microbits depending on your class. So having the Microbit itself is a good starting point. There are a few other elements you need to consider as well. For example, you need to obviously have a PC in the classroom, which needs to have internet connectivity, because the MakeCode environment and the MicroPython environment are both online. So you need a connection. You also need to have an active USB port. And this is something that makes PBL very difficult in schools, because many schools will block the USB ports on their computers for security reasons, and that can make this all come unstuck. So it's worth speaking to your technicians to make sure that there is a USB port available for the students to use. There are various technical ways of doing that, so that they can allow it just for Microbits, so nothing else can get plugged in, or they can just allow you to use it, because you need to get the code from the browser to the Microbit via a USB cable. So it's really important that you can do that. The next element to consider is powering the Microbit. Now, the Microbit can be powered via the USB cable, but the USB cable that comes with the Microbit is very short. It's literally 5 centimeters. So that it'd be difficult to create a Micropet if it's plugged into the computer continuously. So a battery pack is also useful. Some of the Microbit Go packages come with a battery pack, which is really, really useful. They are very, very cheap to purchase, and you need batteries for that. But it's just another thing to consider is you need the Microbit and some sort of power source, and then some way of making that work with whatever device you're working with. For example, if you're making a Micropet, you need to be able to stick the Microbit and the battery pack inside a Micropet. So Velcro tape is very, very useful. You can stick things together and then unstick them very, very easily, whilst gluing Microbits to bits of cardboard can get messy very quickly. So that's the sort of the minimum that you'd need from to do a lot of these projects. And most of our projects in the microcourse book just require a Microbit and battery pack, and you don't need any other electronics. And that's one of the virtues of the Microbit, is it's all kind of housed in the Microbit itself, whilst other devices you may need other electronic devices, you may need breadboards, you need header wires, and that can get, whilst it's completely accessible, it can be quite fiddly to manage and to work with, and you have to deal with all the separate bits of electronics, which can make the process quite messy. But yes, a Microbit battery pack is the minimum, and some sort of making material as well. If you're doing like the oil spill cleaner upper, you could use plastic, cardboard, wood, whatever you've got to hand. Speak to your design and technology or engineering colleagues about that, and maybe do a cross-curricular activity where they might build the boat in a D&T lesson, for example, and then do the programming and electronics in your lesson. So lots of ways to do it. It really does depend on your context and what resources you have in your school. But yeah, there's just some things to consider.
Thanks, Rob. Another question, which I'll briefly address, is a question of whether the resources that we produce are available in other languages, such as Sanskrit. We've actually, if you visit our web pages, you will find 2 links to each of our materials. One is a link to download the content, which is in English. Another link is to GitHub, where you can find the content set up in a way that allows people to create their own versions of the material. So this is something that's very new. We've only just launched this in the past few weeks, but we're really encouraging people to, we're in a sense handing over the keys to the content and saying, if you want to version the materials in whatever way, whether that's in another language, whether it's changing the flow of the materials to better suit your students, you can do that, and you can branch that through GitHub. So we'd really encourage you to try that out and see what you make of it, and also give us feedback. So another question that definitely came up a few times was the theme of, okay, so what if I'm an early primary school teacher? I teach very young children, or maybe I'm not a computer science teacher at all. I teach mathematics, I teach social sciences. What does this mean to me? And I guess, Rob, we're talking about the cross-curricular potential of this approach within schools and how it relates to learners of all ages.
Yeah, so whilst we've talked about physical computing through the lens of computer science today, that you can apply this to almost any subject at all, and it lends itself better to some more than others. But for example, you could teach a physics lesson through this, or a maths lesson, as we mentioned before, and it's just keeping it as simple as possible and using the power of the device in a way which is useful to you. For example, in a physics lesson, you may be teaching about acceleration and about gravity, and so you may already use things like an egg with a parachute, and you try and measure the speed of things, or using ramps with springs and cars rolling down them to measure acceleration. And you can digitize all of that using like a microbit or something similar, so it can be constantly measuring speed and acceleration. You can see those acceleration charts digitally, which makes them infinitely more accurate, and it links together the learning for the physics or the maths to the computer science elements. And using, again, block-based languages, it removes that need for everybody to be able to program in a formal language, and so you can use the context of any subject you like to be able to use physical computing to teach it. For example, if you're doing geography and you want to learn about climate change, you can use the Microbit's or any device's temperature sensor, and then that can log data, the temperature over time. It can measure pollution levels, it can transmit that data. So you've got a very easy, quick way of getting real-time data that you can then look at through the lens of a different subject. So it's really about being creative and thinking about how can we use these digital tools to enhance the teaching of other subjects, and it can teach almost anything. It's just about being creative. We typically focus on computer science, but it covers all of STEM and some of the other subjects as well.
Yeah, thanks, Rob. And the potential there for data science as well, which we're seeing is becoming a real theme that is beginning to appear within curricula. The opportunity to extend into data science, which would go into using that data that you've gathered from the experiment within a mathematics lesson, for example, or a data science lesson, and then that leads, of course, into use of data, ethics, citizenship. So it really does lend itself to coordinating with colleagues in other departments. A really interesting question around assessment, Rob. I know that assessment is a big passion of yours. So how can you assess PBL, particularly given existing assessment methods?
It's a really interesting and complex question. So we have an entire course on this on edX, so please do have a look at that. But it depends what you're trying to assess. I think this is what this boils down to. If you're trying to use project-based learning in a formal assessment framework, for example, like an international GCSE or something similar, it doesn't lend itself to that particularly well, because there are all sorts of just the very nature of a formal assessment in having to sit down in a hall and do an exam on paper. You can't naturally translate that to a project-based learning activity, and so it doesn't lend itself greatly to that, especially when you're doing group work. Group work can be notoriously difficult to assess well, because you don't know to what extent all the different participants are contributing to the final outcome unless you're sat there watching them directly in very, very highly structured assessment environment. So it's very, very difficult to do that. So I think keeping, you can assess project-based learning in terms of learners' progress, and a lot of that is progress by outcome, so whether have they met the success criteria, and constantly getting them to review their own progress and evaluate their performance. We do provide rubrics with some of our projects as well, so that you can see to what extent they've met those learning objectives, and that comes in the form of the lesson plans and a competition rubric which we provide. But in terms of formal assessment, it's a good idea to keep those things rather separate. Not that you can't assess using PBL, it's just it's not typically done in that way.
And Rob, there is also a question of how one, as a teacher who wants to try this out in the classroom, how you advocate for that within your school, within senior management, for example.
Yes, this can be tricky. As I mentioned during the presentation, the project-based learning can be perceived as trivial, and it's worth coming equipped with all of the reasons why it isn't, and it's a really powerful tool to enhance learning and to make learning more engaging. And it's obvious when if you're doing a lesson, for example, with with the Microbit, for example, and the students are progressing rapidly through some of these programmatical concepts and physically building artifacts and expressing this really complex stuff. Teachers will, senior leaders will see this and see that the learning occurring, and it becomes self-evident that it's a really, really powerful tool. And obviously the learning needs managing. You're not just letting them play. It's not like that at all. It is highly structured, it's highly thought about, and that learning journey is managed through using effective resources such as ours. And so it's just a case of being aware of the virtues of project-based learning and be able to communicate them to other stakeholders. And again, we have an entire course on this on edX, which talks about all the soft skills and how to work with stakeholders inside school and outside of school. And there's lots of different ways of angling this, working with other department leads through cross-curricular projects, having collapsed timetable days, turning it into, or gamifying the learning through competition. So there's lots of different levers that you can pull and terms that you can use in schools that will let people understand what project-based learning is about and let you demonstrate its effectiveness.
Yeah, thanks, Rob. And I think another question that's very much related to that is how can you make the teaching learner-centered? And I think there's it's perhaps interesting to reflect on that in terms of the changing role of the teacher within a PBL classroom compared to what you might experience otherwise. Yeah, so the notion of sort of learner-centered is that's the whole point of doing project-based learning, I suppose, because you're not as a teacher, you're not just broadcasting information to the learner and expecting them to absorb it all and learn it. It puts some responsibility on the learner to figure out the problems that you're presenting them. You've given them the tools available through through previous learning, but in the projects, you're then enabling them to demonstrate and apply that learning to solve a novel problem. So you're giving them these success criteria. So, and you're giving them some of these abstract challenges that they need to work out how to do that. And they do that independently. So that is where it becomes learner-centered. And it's not them just working it out kind of on their own. You're providing them with the tools and the scaffolding to do so. And then they're restructuring all those different elements that you've provided to them previously into something novel and creating this artifact where they express these complex elements. So it is very much learner-centered, and even when they're working in collaboration with other learners and they may be focusing on different elements, it's still very much learner-centered because they're having to collaborate and solve a big problem, and they're all becoming different cogs within that machine. And yes, it's very much learner-centered. Not to say that you couldn't do, again, these things outside of a group environment, and it still is very much learner-centered because you're not giving them just a route to follow. You're not just providing them with a book to read with some questions. It is, here's a problem, you need to think and work to solve this, and that's where the learner-centric bit comes from. Fantastic. So I think another one, Rob, that I think would be great for you to answer, particularly given your background in assessment, is the question of does PBL improve test results, which I think is a really interesting one, isn't it? That's obviously at the forefront of teachers' minds.
Absolutely. And whilst there is very little empirical evidence to suggest that it does, think of it as a teaching tool to make students more confident at applying programming concepts. And so I went through this a little bit earlier in the presentation, where if you're teaching, let's say, for example, you're doing computer science and they have to answer programming questions. If you're teaching them the concepts in the abstract, it can be very difficult for some learners to apply that concept in a different situation or using different data. And that's what makes computer science difficult. There's very much a bell curve of students that get the construct and then can apply it in any situation. Many students understand it in the concept that it's provided to them initially, but struggle to reapply it later on. And it's the same with maths and physics as well. And that's what makes them slightly more difficult subjects. Whilst relating those computational constructs to a real world thing like temperature, as I mentioned in the presentation, it helps it sink in and become more real and more concrete to that learner. They can relate to it more directly, and then it helps them understand how that concept is applied to the real world, and therefore it builds that foundation of being able to apply that theory in other situations similar to that. So it creates that that relational model where they can apply it in different situations. And so it's not a sort of if they do PBL, their grades will definitely improve. It's more, it gives them a much better chance of being more confident applying computational constructs to real world problems, as well as all the other skills that we talked about as well. So it just makes them more confident in doing stuff in the real world. And ultimately that's just as valuable as formal assessment results, because if someone can only answer exam questions with programming skills, that's not very useful. And you see this with that LEET code and these sorts of tools where you get very good at solving exam questions, but not very good at programming in the real world. So it's this tries to sort of combat that and makes it so it is relatable to the real world and makes them better at the creative task of programming.
Another question that is very pertinent at the moment is around how do you facilitate PBL if you're carrying out online learning, particularly with the current epidemic, with many schools out of action and students working from home? What's the potential there for using PBL?
That is a tricky one. Obviously, if everybody's working from home, then they can't do group work. Not that you don't need to do group work. It's more of an issue of access to the technology. So if you can send all your students a Microbit or a Raspberry Pi or something, then fantastic. But not many schools can do that. And obviously not all students are going to have this equipment at home, and if they don't have access to the hardware, it makes it very difficult. Not that you can't do PBL projects without hardware, because you can. For example, you do the MicroPet project just in the simulator on MakeCode and in MicroPython as well. So there are ways of not doing the physical element, but that does detract from the efficacy of project-based learning as a pedagogical tool. So yes, it does make it very difficult. It can be done, but you're making a lot of sacrifices to do so.
And I think perhaps the last question, which I hope will then mean we've covered most of the comments that have come in, is around how can teachers get training in PBL. Now, of course, as we've discussed, and I'll include a link to this at the end, a mention of this at the end, we have the 4 courses available through the edX platform, which are free to access on called Teaching with Physical Computing. But there's also, Rob, I suppose, an opportunity with PBL for peer-to-peer training and really working with other teachers in your community once you've developed this expertise to spread best practice.
Absolutely. So we have we work with groups of groups where teachers come together to learn about or to get better at teaching, so communities of practice, and it's always worthwhile sharing your resources that you come up with if you've written a series of projects contextualized to a particular geographic area or a particular subject. Sharing is caring. Do work with your colleagues to do these sorts of things, and you can also work with other schools and run inter-school competitions. We've done that in the UK, where we've had a competition between sort of 20 odd different schools all competing on a IoT smart streetlight and the boat oil spill cleaner upper project as well. So there's lots of ways of collaborating with your peers around this and supporting each other mutually.
Great, thank you. Okay, so as I say, I hope that we've covered most of the questions that have been raised within different groups there. Thank you all for submitting them. Rob, if we could move on to the next slide, please. If your question hasn't been answered, or you think of something after the event that you would like to, that you have a query about this approach, if you want to raise that with us, please do consider enrolling in our edX courses and raising the question in the course forums, which Rob or other users can help address. So that's a great way of relying on the community to help you through this. Next slide, please, Rob. And just a reminder that if you've enjoyed today's event, you can explore the themes that Rob has discussed in your own time and in more depth through our edX program, Teaching with Physical Computing. It's free to access, it's self-paced. The length of the course, which you can see here, is 12 weeks at 1 to 2 hours a week, is very much a maximum. It assumes that you are practicing your learning within the classroom. But if you simply want to go through the content end to end, you can do that within 2 or 3 evenings within a week. So it's very much up to you as to how you work with that material. You know, we'd love to get your feedback as well after each course. So do tell us what you think, what works for you, what doesn't work, how you think we can improve. Thank you, Rob. I think we'll move on to the next slide. Okay, so it just remains for me to thank you all for making the time for being with us today. We've really appreciate your joining us, and I hope Rob and I both hope the training has been valuable to you, and we look forward to reading your feedback from the feedback forms. And once again, I'd like to extend our thanks to CBSE, to Dr. Saha, Mr. RP Singh, for enabling this event. We really appreciate their support and collaboration on this. And also to my colleagues, Apurva and Surya, for making this work. We really appreciate your efforts on that. Thank you, everybody, and have a good rest of the day. Thank you.